Good evening and welcome everybody. This is Obi-Wan Peds for Simplex Pachinko. We are a little bit late tonight. Sorry about that. And also took the Wednesday or Tuesday night off here. I've been trying to grade papers and whatnot, and I'm just not catching up. It's not going well. Gotta be honest. So hope you all are having a better week than I am. Here we're looking at an example from last week. Blainlin came up and asked for trying to find the eigenvectors and eigenvalues for a particular transformation matrix. So we gave him a transformation matrix, 3x3, probably not the best idea. And said we want to find the null space solutions, which are going to be those vectors x1, x2, x3, which satisfy the multiplication of a times x vector, getting us a 0 vector. So that worked out. We got one of the solutions. So our first Xi vector, or the first x vector, which is going to be our eigenvector, is the one that we found here, corresponding to an eigenvalue of 0. Basically, you set then the transformation matrix times our eigenvector is going to be equal to 0. And normally you'd have along the diagonal like your individual values minus lambda. So here would be 1 minus lambda, 1 minus lambda, and negative 11 minus lambda. But they were 0, so it was just the transformation matrix itself. So our first vector, which is in the null space, is right there at the bottom right, negative 2, 3, and 1. And just to verify, we're going to plug those values in and multiply our transformation vector times that vector to see if we do in fact get the right thing. Because it's been known to happen before on this channel, especially. We do not get the same thing that we're supposed to. And if we don't, I'll figure out why. It might take a while. So 1, 2, negative 4, 2, 1, 1, negative 1, 3, negative 11. Multiplied by negative 2, 3, 1. I mean, literally it should, because that's how we created this thing in the first place up at the top left here. So, in theory, it's how we did it. Oh, that's off the screen. Alright, when we do this, we get 1 times negative 2. That's not what I said at all. Hey, Loims. How's it going? Plus 2 times 3 plus negative 4 times 1. Second row is 2 times negative 2 plus 1 times 3 plus negative 4 times 1. That is not it at all. No. 1 times 1. Come on. Come on. There we go. How are things going? Yeah, no, everything's fine. I just got overworked. Decided to take the night off and correct papers. Didn't get very far. Which is too bad. Alright, up top we got negative 2 plus 6 minus 4. Nice. We got negative 4 plus 3 plus 1. Nice. And we got a 2 plus 9 minus 11. Awesome. Those are all 3 zeros. So yes, we do in fact get a member. This is a member of the null space. Decimated your final exam. Nice. Which yeah, which exam was that one? Calc 1? And I mean, it's kind of a stupid break. It wasn't even really a, like, break. It was, I needed to work on actual work instead of having fun with you guys online. There will be a time at some point in the future where things are going to change a bit, but I hope you all can still hang out and whatnot. I know over the summer, since I'm not working on a daily basis, I'm going to try to do more day streams, get some other stuff in there, so. Yeah, I think my roommate in college took, maybe not that exact class, but it was called formalization. I believe the average score on the midterm was a 39. That would be the full computer science level class. Go for it. I also have a potential JavaScript idea for a custom theory for exponential idle. So I threw it in their Discord, and all I got was a couple of reactions of eyes. Yep, I have. McNugget numbers are always a very strange concept to think about, because it's like, you know, I mean, this works for any combination of stuff, right? It doesn't have to be specifically McNuggets. Yes. So I don't remember what the exact numbers are, do you? I mean, I could probably also look it up online, because, you know, I got, like, information. Six, 9, and 20. Okay. Also known as the coin problem, because yeah, okay. So 6, 9, and 20 are numbers in question that we wanted to create all the rest of the numbers out of. So realistically, right, what we want is 6 times x plus 9 times y. Come on now. Plus 20 times z is equal to n. Tablet, please. It's probably not the tablet's fault. I'm going to blame whiteboard. So, like, I don't know of a way to prove this, by doing linear algebra, but yep. And of course I have the answer right here because I just looked it up, but I mean, not intentionally. It was just with a finite number of examples. Megalomorph! Yeah. That's fair. So the question was, could you use linear algebra in order to solve it? Just gonna cut the volume a little bit on that. Unless, of course, you all are fine with it, but I can't hear myself over it. That could just be my headphones. No, that's alright. So, I mean, you're looking for the span of the vector, is what really we're talking about. Or the three vectors. But again, then you're limiting also. Yeah. Right, you're not allowed to do any linear combination. It just can be the non-negative, and it has to be limited to integer values of x, y, and z. I gotta tell you, Megalomorph, I was not quite very good at the upper level linear algebra. Mostly because my professor made it up. Sure, we'll go with that. Alright, so x, y, z, and n all have to be positive integers. Well, no, okay, they can be 0. Fine, union 0, I guess. I don't know. Do we have a notation for that? Natural number. I mean, it's also natural numbers union 0, but or does 0? Or are you one of the people who includes 0 in the natural numbers? Geck. Oh man, I could teach you the Simplex method of for linear programming. If I can remember it. No relation. Oops. I've already taught you the OBI method of solving absolute inequalities. Right, target value is -1, variable value is 3x. We have to be two away to either side, and then we're allowed to be there because it's greater than or equal to, and then it's greater than or equal to, so we have to go outside of this because that's the distance. And then because it's 3x, we just want x. Everything has to be divided by 3. Which means that we can take this, go like that. X, this is going to be 1/3, this is going to be -1/3, not that that matters any. This is going to be -1, and then we shade out from -1 and out from 1/3. Et voila, we have the solution. X is going to be from -infinity to -1, inclusive, union, inclusive, 1/3 to infinity. Done. So -3 divided by 3. Oh, this one. Yeah. So what we're really saying is what's the distance between 3x and -1 is going to be 3x minus parentheses -1. Ew. So yeah, this -1 here really is, this -1 here comes from this thing because we're subtracting a negative, makes it plus. I really should have done the positive version first, but I don't know, I guess I was probably just showing off. Yeah. So if we have, I gotta get an example. Decent. Ugh. Now, it has been years since I've done this, so. That's big. Can we get an example? All right, there we go. Alright, so our objective function is to maximize z, which is equal to 40x1 plus 30x2. And constraints So typically this is given as like, you know, your objective function is like an output of a factory or something like that. And the constraints are going to be like the amount of resources that you have to do stuff with them. So in this particular case, it says x1 plus x2 must be less than or equal to 12. 2x1 plus x2 must be less than or equal to 16. And, okay, both x1 and x2 have to be greater than or equal to 0. So it's not really that surprising. So we go through and we say we want to make a tableau out of this, which has in it our 3 equations running down, or the equations are running across, the variables are running down. So we have x1 here, x2 here, y1, y2, let's not do y. I'm going to go against the grain of what this thing says. So we do S1 and S2, and then Z. And we have a secondary column. Okay. And then we do the same thing kind of that we do on the linear algebra stuff that we were doing before, finding eigenvalues and eigenvectors, where we're going to have our constant over here. And basically this is going to be our equality sign here. So our first equation was that x1, so there's one of them, x2, one of them, and so there's going to be a slack, oops, slack variable, which says that we're going to say, we're going to pick up whatever the extra is here that we are less than. This is going to force this to be equal to 12. So pick up the slack, and we're just going to say no S2s on this one, no Z's on this one. Our constant is going to be 12. On our second one, we had 2x1 plus 1x2, no slack 1s, but this time we're going to introduce slack 2 for, again, being less than or equal to, converting that to being strictly equal to 16. If anybody wants to stop me at any point, feel free. Alright, and our other one here, Z, is going to be 1. And we're going to move everything to the other side because our x1 and our x2 are the only things there, and we want them to be all on the same side as the Z. So negative 40 x1 and negative 30 x2, zeros on the slacks, because again this is equal to at this point, and no, okay, and no constant. Our goal here is going to be to do row operations just the same as we did in linear algebra. Our goal eventually is to get zeros here, and in some way, shape, or form, we're going to get an identity matrix here. An identity matrix, not the identity matrix. So it could be 1001, or it could be 0110. We're not going to be picky. The point is, though, that only one of the x's should be on each row at any given time. Okay. So, what we do, we're going to identify the column that has the highest negative entry. So that's going to be 40 in the first case, or negative 40 in the first case. So this is going to be our pivot column. And then we're going to divide the entries in the rightmost column in our constant by the entries that are in the left column. You still can't see my cursor. Damn it. See, you told me. Here we go. So we're going to divide our constants here by the stuff that's in x1, and because that was our pivot column, right? The stuff that's in this column here. We're not going to pay attention to this last one because it's not going to count. We're trying to figure out which x it is that we're trying to hold. It's a terrible word to say it, but which one are we trying to solve for to get 1, and which one are we trying to eliminate to get 0? So here we end up with 12 over 1, which is our stuff in this left column here, and here's 16 over 2. Okay, so the smallest quotient that we're going to get out of this is 8. We don't do this one at all. Smallest quotient so that means that our pivot element is going to be 2 for this one. So we're going to take this particular element, and everything is going to be based on that one. All right, we use standard linear algebra for the rest of this. So, you know, the other steps that are here, not literally the rest, but you get the idea. I hope. All right. So we're going to say that on our next step, we want to take row 2 and divide by 2, which is the element that we're dividing through here. This is going to get us a 1, a 1/2, a 0, a 1/2, a 0, and an 8. And now we're going to take row 1. What do we do to row 1? Well, we're trying to get a 0 in that first one. So we're going to take half of row 2 and subtract it from. Let's go the other way. Subtract it from row 1. So on this next step, sometimes when we're doing it with college algebra students, which used to be one of our big projects at the end of the semester, because most of the time they need linear programming more than the calc students, what we'd say is, okay, everybody come to this level and then just copy everything else. It just all stays the same. And then on this next step, we'd say, what do we do with this in order to get a 0 here? Right. So, or, you know, when I wrote everything down as 1, 1, 1, 0, 0, 12 with the 1, 1/2, 0, 1/2, 0, 8, so that on the next step down, on the next time we copy it, we'd be able to see it all. It's so tedious. Linear algebra students would be like, come on. All right, so subtract half of row 2. This is going to get us a half here. 1 minus a half. 1 minus 0. 0 minus a half. 0 minus 0. And 12 minus 8 is going to be 4. Okay, and then for row 3, we want, right, so we want into row 3, take row 3 and subtract 20 of the prior row 2. So half row 2 into row 2. Williams, did you have an actual question? I mean, I know you already said it, but anyway. So 20 times row 2 is going to get us 40 plus this one. Or yeah, we're good. No, plus. We just need plus. So 40 plus minus 40 is going to get us the 0 there. Yeah. Negative 30 plus 20 that we get from the above is going to be a negative 10. So now this one's going to be our pivot column for the next step. And then above, we're going to worry about this in a sec. So this is going to be 4 divided by a half and 8 divided by a half. And both of them are just doubling, and the lowest value is going to be this one. So this is going to be our pivot element for the... I did that backwards. Yeah. All right, anyway. So we know that that's going to happen on the next time down, the next time through, but for right now, we're just going to say, okay, keep going. This is going to be, right, row 2 had 0 for the first slack variable. This was going to be 20, row 2, so 20. It's going to be that for our slack. We still get 1 for Z. And then on the constant column, we get 20 times 16 is going to be 320. I'm okay to continue this one just because we're pretty close to the end anyway, but... Okay, so then we take this and we say how many of these plus the bottom row is going to get rid of all that stuff. We're going to do into row 2. We're just going to do row 2 minus row 1. And into row 3, we're going to take row 3 and add 20. Row 1. 20 again. Interesting. Okay, and then here we want to make sure that this is going to be into row 1 is going to go twice row 1. 0, 1, 0, negative 1, 0, 8. 1. Right, because we're just going to add down. That's going to be a 1 still, so it doesn't matter. And then row 2 minus row 1. So a half minus a half is going to get a 0 there. 0 minus 0 is 0. Something's not right. 1. That should not be a 0 here. Slack 1. We did row 1 minus that. Yeah, so it's just 1. Okay, we're good. So this is going to be a 2 now. Yeah, anyway. Okay, so this one over here is going to be row 2 minus row 1, so it's a half minus a negative half is going to get us 1 now. 1. Whatever that was. Z still has none in this particular section, and then 8 was going to be row 2 minus row 1 is 8 minus 4 is 4. Bottom row we got 0. We've got 0 intentionally. Slack 1 is going to be row 3 plus 20. Row 1 is going to be 20. This, because it was affected by our slack 2, or sorry, since row 1 was affected by slack 2 before, it is now going to also affect the slack 2 on the bottom row. So now this is going to be row 3 plus 20, so 20 plus half of 20 negative, so 10. 1. And then our constant is going to be 320 plus 20 times 4 is 80, so that's going to be 400. So what we've got now, unless I'm very much mistaken, is that everything here is done. 2010, 1, 2, negative 1. Oh, shit. I missed one. Here. Again. No. That was fine. This, yeah, here. Here. So we take row 2 minus row 1 on this one. Right, because I did row 1 is 0. So that one is a negative 1. There we go. So row 2 is 0 minus row 1 is 1. Gets you negative 1 down here. Okay. Negative 1, 104, and 0, 0, 20, 10, 1, 400. Cool. Okay. So the actual equation that we get then is that our objective equation z is going to be 20 slack, no, let's start the other way. Z is equal to 400 is going to be our starting value, our constant, minus 20 slack 1 minus 10 slack 2. For every unit of slack that we have in equation 1, or inequality 1 from the very top, then this ends up reducing our objective function by 20. And, you know, if it's dollars or whatever it is that you're doing, and every unit of slack you have in equation or inequality 2 ends up having a net negative effect of 10 units to, yeah, to our objective. So then we've got our individual, yeah, okay. So here, ideally, what we want is that slack 1 equals slack 2 equals 0, right? This is the ideal situation. And when that happens, then we end up getting an objective value of 400. So z is 400. And if you look at the stuff up above, this also tells us that in the first row here, this is going to be x2 plus 2s1 minus s2 is equal to 8. And x1 minus s1 plus s2 is equal to 4, which again, in the ideal scenario, this stuff is all equal to 0. So you just get x2 is 8, x1 is 4. So it's like this really, I mean, overall, generally speaking, it is pretty nice to make this work. Yeah. X1 is 4, x2 is 8. So we can find the ideal scenario, and it makes it work. There is the possibility... No, never mind. So I can't think of an example, but there might be a possibility where you end up with like you have to have slack, but I don't think that that's the case, or maybe in more variables if it's linearly dependent. If there's something that ends up canceling out somewhere and one of your variables goes away, right, then you have to estimate what's going to happen based on what your slack's going to be. But generally speaking, right, what's happening here is that we've got these inequalities. x1 plus x2 is less than or equal to 12 is going to get us a line where if we call x1 x, I guess, and x2 are like y variable, this is x2 minus x2 is equal to 12 minus x, so it's going to be like that. We've got 12 and 12. And then in our other direction, we've got x2 is equal to 16 minus 2x. So let's see, 12, 6. 4 is that distance. It's pretty close to there. So half that distance is 8. It's going to be about 2/3 of 12. No, 3/4. Yeah, give or take. Okay, so we've got the two inequalities here, and it says that we need to fall somewhere in this space, right? Because we need to be less than both of those restrictions. Our x2 values need to be smaller, so that needs to be lower than or along the lines. And what we did was we actually said, let's take a walk here along these lines. And which points do we actually hit here? Okay. So I don't remember which one we did. We zeroed out x1 first, which makes us go to 4 in the x direction. We went to 8. Because here, if you notice, right, this is a half. 4 divided by a half gets us 8. So this is our x2 value. Oh, that's wrong. What the hell? Was it this thing? Was it the other one? Right? Was it this? Is that the reason? Because when we did this one, this was also 8. Crap. Let's see, if this was at 16, it's going to go down 2 to get to 14 at 1. At 2, it's going to get down to 12. At 3, it's going to get... Okay, the difference is 4, so it's going to take 4 to catch up. Yes, okay. So then by the time that's reached 4, yes, okay, this is 8. So this is going to be 4, 8 here. That's the point that we ended up getting eventually. This was 8, 0. This was 0, 12. And this was 0, 0. Okay, I'm better. So I'm pretty sure that what we did was we traveled along this line here to get to 8, 0 first. So we found where x1 was going to get us an 8 value. And then we traveled along this path, which mixed both x1 and x2 in how we did the process that was here. And that ends up getting us to 4,8, which it turns out is the optimal solution. So it's called the Simplex method, I think, because I don't know exactly. Megalomorph, you can chime in if you know. But I think because it applies to, like, if you were doing this in 3-space, generally speaking, you're looking at this in terms of a simplex, and you're trying to travel along the edges of the simplex. So in here, you're kind of doing the same thing, but it's not really like... It's a simplex of these particular equations, or inequalities, rather than like a true two-dimensional simplex, which is just a triangle. I think that's right. But I could be just talking out of my ass, so it's okay. So the point of all this stuff is, like, the points end up giving you the individual locations where it's only actually possible to hit the best values based on the constraints and the objective function. Like, anywhere along each of those lines is going to be growing along one of them and shrinking along the other, potentially. And so you end up with, like, it's going to take away from the objective function, or it's going to add to the objective function along the entire line. And so it's not going to reach a potential maximum or minimum until you reach the next point. And then again, you just reevaluate. It's kind of like doing a gradient in calculus, but you're doing it like algebraically step by step instead of saying, like, what is the overall gradient of this thing? How can I reach a maximum value? Anyway. So yeah, if you're looking at it in terms of, like, how do I find the McNugget numbers for... How do I get the McNugget numbers for this? I don't... Oops. Yeah. I don't know of a way that you could do it just using linear algebra or simplex method. So, I mean, the problem is really that you have only one equation. It has a bunch of constraints on it, but yeah. Spoilers. No, so the way that we did it, my spouse actually had this as an interview question that she was giving high school students, or college students. No, it's 43. Oh, I see. Yeah, so she was giving this to prospective interns, basically. And even if somebody was like, oh, yes, I already know the answer is 43, she'd be like, okay, well, how do you go about solving that thing? Or she'd be able to like throw out a different number. Like, you know, 5, 8, and 16, or not 16, 5, 8, and 8, 18, sure. But yeah, basically, you're saying, like, what are you covering for everything? So, the way that I did it in my head was I said, okay, you get 6, 12, 18, 24. So this is all of the just multiples of 6, right? And then the next one's all multiples of 9, so that's easy enough. So 9's in here. 18 is already there. 27. 36 is already going to be up there. 45. And then 20 is just going to be, okay, that's 20, 40. $60, $80. I guess 60 is already taken up above. Yeah. But I mean, basically, I'm just basically doing like a sieve of Eratosthenes in this. I'm looking at all of the multiples of them, and then going, okay, from these multiples, I can go like this, or from these multiples, I can go like this. And so, what was I doing? It ends up being like I can cover every multiple of 3 that is bigger than right. So 15 I can get from the combination of 6 and 9. 21 I could get from the combination of, or can we not get 21? Is that one of them? 669, thanks. Right, yeah, 12. 12 and 9. It's right there. Should have realized it. It's right there. So yeah. I can get all multiples of 3 using this particular setup. And then it was, okay, how else can we get, like, all multiples of some other number? And so I was able to, you know, parse out a few different ones that would work like that. I think I also thought about using more strictly like linear algebra type stuff, where we're saying that might be able to use like binary representation. Let's see. So if we know that it's going to be less than 100, then let's just even use 6 bits. I mean, that's only 64, but right? 1, 2, 4, 8, 16, 32. Okay. I mean, we already know the answer, but nonetheless. Okay, fine. It's like, I know that 6 is going to be 0, 0, 0, 0, 1, 1, 0. I know that 9 is going to end up being 1 and 1 like that. And I know that 20 is 0, 0, 1, 0, 1, 0, 0. This may not work, by the way. I'm just Yeah, yeah. So these essentially become our vectors. It's not the best way to put it. Might work. So like 2xn is equal to 1x sub n plus 1 for all positions for this stuff. And then you basically say like, okay, I'm gonna get, you know, 0, 0, 0, 0, 1, 1, 0 times a plus 0, 0, 0, 1, 0, 0, 1 times b 0, 0, 1, 0, 1, 0, 0. Ew. Did not fit that in the space allotted. 0, 0, 1, 0, 1, 0, 0 times c. It doesn't quite work, right? It's no. Yeah, it just I don't know, I just felt like there was sort of a way to do it, but yeah, it's fine. But I mean, that's sort of what I'm doing, like, in my head, I guess, is... Yeah, just start taking all of them out. So if you get all of the numbers 1 through 100, let me pull up something easier that I can actually do here. So, alright, if I just steal a 100 chart online blatantly, they're gonna get me at the copyright office. Oh man. Oh, that's dangerous. Let's mute this a second, just in case something goes horribly wrong. No, okay, good. I was just thinking, like, what if it posts, like, you know, the last thing that I copied somewhere and I have no idea what that is. Okay, so for this, right, we do, I know for a fact that, right, 6, 18, 24, 30, I know math, 36, 42, 48, 60, 54, This is the other thing that I really like doing with this is you can end up with the Knights hops. Add 6 here. That's 84, 96, and not 100. Right, so if we go like 6 is red, and then we go shh. You're not supposed to see that. Alright, and then the 9s, we go like this. We could do 9, 18, 27, 36, 45, 54, 63, 72, 81. Way easier. 90, 99. And then 20s are going to be just 20, 40, 60, 80, 100. Yeah. So then we can go 6 from all 20s. So 26, 32. That's going to be fun. 38, 44, 56, 50, 68, 80s duplicated, and then 26 down, 1, 2, 3, 4 back. Shh. 74, 86, 98, 2, 3, 4, 92. Right, and then we go 6. Then we can also go 6 from 40. So 46 is then going to get 52, 64, 58, 70, 76, 82, right? 94, and then back to 100 again. And from 60 gets 66, 72, 84, 96. We already got all those, right? This is just all copy paste from before. All right, because it was a red by itself. 80 gets us 86, 92, 98. That's all done, and then 100. All right, so then 6 away from all 9s. It's going to get us our 15. So I'm taking 6 from every single multiple of the other numbers. Wow, dude. Wow. All right, so yeah, 6 away from 15 gets us 21. 6 away is 27, 6 away is 33. But what I'm doing is I'm actually just using a pattern. And I'm saying, like, basically I just took 21 and I added 12 to it because that's down 1, right 2, and it's so much easier to just get that. $69 plus 6 is 75. Wow. 75, 87, 99. Already got it. Then what else? That was 21, 21, 27, 33, 39. All right, 45, 51. 57, 63, 69, nice. 75, 81, 87, 93, 99. Okay. And then 6 away from all 18s. So again, here we're just going to add 6 to all 18s. 24, 30, 36. We're already on Yeah, well, it's already a multiple of 6. Right, never mind. 27, add 6, we get 33, 39, 45, 51, and then we're on to another track. So we already got all this. 36, 42, 48, so that's all good. 45, 51, 57, we already got them. 63, we already got them. Yeah, so we're good. We're done now, or at least with those. Right, all the rest of these all end up having combinations that we already found. So then we say, okay, from 20, we could add a 9 and get 29. And that gets us 38, 47, 56, 65, 74, 83. Yeah. All right, 40 is going to go diagonal again. So 49, 58, 67, 76, 85. 60 going all the way through. 80 going all the way through. And 100. And then from every other number we've ever gotten before, we could also add a 9. So go diagonal down left from those. So here we've got 26. Add 9, we get 35, 44, 53, 71, 62. Let's see, we've got all these along this diagonal. Along this diagonal, we've got 46 as our first one. So that crosses out 55, 73, and 91. This one we've already got. This one we've already got. 50, 59, 77, and 95. 70, 79, 88, 97. That took out all the rest of those. So now the largest number we have left is 43. And unless you can find another way to find it, which obviously we can't, it's not actually possible to find any other way of getting rid of that one. We do find that 41 will not be had because 41 can be made because we already got 32. So add 9. 26 going that way, 9 going that way, 6 going that way, 32, 12, 20s, 30s, 40s, 50s. Cool. So yeah, we've got this little section here. We've got close enough. We've got these two numbers here. We got these numbers all down here. Got these numbers here. Those 3, 2 and 11 and 1. So these end up being our numbers. Let's just check real quick because I want to make sure that this is all of them, right? So 1, 2, 3, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, 19, 22, 23, 25, 28, 31, 34, 37, 43. Yep. Yeah, we already got 60. Oh, yeah. I left it blank, but 52 plus 9, yeah. We got 61. That was me just screwing up. Yep. Okay. Woo! Go for it. I mean, Civa Veritas these, but... We'll see how much brain power I got. That's fine. I guess I should not be sitting in the, Final Fantasy Remake category, at least not yet. New 100 grid. All right. Woo. Oh, somebody might find it a bit misleading. Be like, what are you doing? Yep, so what are the core numbers this time? Every 1, every 2, every 3, every 4, every 5. That one? So our first pass through, we light them all up. And let's just assume that... oh, look, they're lit up. Alright, our second pass through, we hit all the even numbers and turn them off. Right, and then the next one, we're going to hit all of our multiples of 3, and then just reverse whatever is there. So this is where it gets tricky, because I'm going to actually have to... okay, so here, these are all multiples of 3. Let's see, these are all multiples of 3, going back that way. These are all multiples of 3, going back that way. These are all multiples of 3 going back that way. These as well. These as well. And let's see, do we miss any? So 1, 2, 3, 1, 2, 3. Okay. So those are all multiples of 3. Now, so yep. Anywhere where there are 2 that are matching, it's basically like double negative, so they turn on. So these are back on again. The ones that are the intersection of divisible by 2 and divisible by 3. Or in other words, those that are divisible by 6. Which is also something to think about when we get to 6. Okay. Any others? I think we're good. Nope, 6. Duh. Alright, I think we're good. So now we get all multiples of 4. So that's going to be, come on now. 4, 12. 8. 4, 8, 12. 16. 20. 24. 28. 32. 36. 40. 44. 48. 52. 56. 60, 64, 68, 72, 76, 80, 84, 88, 92, 96, 100. And again, anywhere where there are 2 things that are hitting, we're going to turn them back on. Or the result is that it is on again. Okay, so then multiples of 5. So now this is going to be 10 and 50 and 70 and 60. We're all going to be off again, or turn back on again. 75 is back on, 45 is back on, and 15 is back on. Maybe. So 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, 66, 72, 78, 84, 90, 96. So 24, 12, 36, 48, 30, 72, 84, 96, 90. Okay. 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, 98. I think we're good. All right, then 8. 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96. This gets rid of 80, or turns back on 80, 56, 40. Okay. I mean, just like any color at this point probably is a good idea. All right, so then 9 is going to be 9, 18, 27, 36, 45, 54, 63, 72, 81, 90, and 99. So that turns back on 99, 81, 72, 54, 27, 18, and 9 itself. All right, 10 is again just going to be yet another line down through like this, which then gets 20, 60, 70, 90, and 100 back on. Okay. 11 is going to be right along this diagonal. Oops. Not 100. Which gets 88 here, 77 here, 66 here, 55 here, 33 here, and 22 here. Right. 12 is 12, 24, 36, 48, 60, 72, 84, 96. So 96, 84, 48, 36, All right, 13, 26, 39, 52, right? Yes, 52. Yeah, 14 or 13 times 3. 4. Wow. 13 times 4. Deck of cards. All right. 65, 78, 91, and that is it. $78, 65, 39, 26. All right, let's get just the next couple here, and then we'll see if we can spot the pattern yet. I guess, do you know the pattern is the other question. Which ones are going to be left on at the end? So 28, 14 is 42, 56, 70, 84, 98. I guess you've probably also done this by programming, or maybe not yet. Makes it so much easier. All right, so 15, 30, 45, 60, 15, yeah, 75, and 90. Okay. 16, 32, 48, 64, 80, 96. So 80's back, 64 is back on. All right, 48, 32, back on. And 16's back on. Right. 17, 34, 51, 68, 70, 85, and over 100. So 85's back on. 68, 51's back on. 34, back on. Okay. So here's the thing, right? Look at the next numbers. All of the next numbers until what are going to turn off. Because they're not multiples, they don't have multiples of each other. They're too close together. So all numbers from here on until what will be turned off. So we just did 17. Right. So here we're doing 18 next, right? The next multiple of 18 is going to be 36, and then 54, and then 72, and 90. Right? So all this other stuff that I'm doing it down here, it's kind of window dressing. It's not going to matter that much. Every other number that we're going to do, right, is all going to turn off until we get to 25, which is going to be flipped back on. But then every number after that will be turned off again. We had 18. which flipped everything off up until we get to 36, at which point this now will be flipped back on. 37 was prime, so that's going to be flipped off. 38 actually was a multiple of 19, so that gets flipped on at 19, but then off again at 38. Seeing a pattern yet? Yeah. So 1, 4, 16, 25, and 36 are the numbers so far that we have flipped everything off and back on again. When we reach them, they flip on. But the rest of the numbers ended up getting flipped off all the way through. Oh, okay. Well, this should do it. Oops, missed one. 9. So 1, 4, 9, 16, 25, 36 are all turned on when we get to them. Now the interesting question that you're going to ask yourself is why? Because it took a while for me to figure out why it was that worked the way it does. Oh yeah, that's a very well-known pattern. Yep, there you go. So again, the interesting part is when you start looking at this and saying, okay, now why is it that it's the squares? Yep. So 49, 64, 81, and 100 will all be on at the end. All the other numbers are going to be flipped off. This is one of those, Sunil Singh moments here where you're just like, oh. I mean, it has something to do with it, yeah. Yeah, so you look down at all of the numbers that evenly divide into all the rest of these numbers. The primes are, generally speaking, pretty easy to figure out. And in fact, if you only do the primes, it's like, oh, well, yeah, clearly. But then when you start looking into the other numbers, it also becomes fairly clear what exactly is happening there. Nice. Oh, okay, yeah. Well, all right then. Sure, why not? I was at on somebody else's stream a couple of days ago, and I had to go away to lurk to go to my karate class, and when I got back, 10 messages were popped up there. It was like, "Hey, Obi-Wan, you still here?" I'm like, "Oh no, what happened?" So, turns out I won a humble bundle. It appears that I won Control Ultimate Edition, which I was honestly I was going to pay for it, but all right. I take it. So I've already paid for the original, and I didn't get the DLC. I was thinking about getting the DLC, but now I don't have to. No, but I know that I have to go back and play at least a couple of why am I blanking? Alan Wake. There we go. Ooh. That's going to make it a lot easier to play, too, on my somewhat newer stuff. Oh, yes, I did also play Max Payne 1 and 2. I didn't play the third one. Were there more than that? Okay, so anyway. So prime numbers, easily enough, right, are going to have just those two prime factors. So you get 1, which flips all of them on, and it flips every number on. And then you get the prime numbers, which get flipped off when you get to them. And those are the only times you get to them. Blaine, good evening. Congratulations for finishing the class. How'd you feel? So, yeah. So, Loims, you then also have to figure out, like, okay, well, not all of them are just going to be the square root and 1 and the number itself. Hey! 84 is great. Might not be up to your standard, but it's alright. I am happy when my students get B's. 94. Well, hell, man. You got an A. I know, everyone was getting worried, like, oh no. See, you know what you're doing. Everybody's making mistakes. It's fine. Don't worry about it. You did great. Congratulations. All computer science next quarter. Yep. All right. I mean, look, if you're ever feeling down on yourself on like how you're performing in your math classes especially, go talk to the professor and like ask them what's going on and how everybody's just generally speaking. How's the rest of the class doing? No, I know. And it's kind of an internalized thing, right? Because like all through elementary school, I was always like super A student, getting A's in everything, and then like I started falling off and getting B's, and I'm just like so worried. But it didn't really matter overall. People still wanted to hire me. Even after I ended up getting like a fair amount of C's in college. Only in a few select classes, but still. I got a fair amount of C's in college, but I turned it around in my junior and senior years. My now spouse was really helping me understand stuff a lot better than I was beforehand, and I ended up getting like pretty much all B's again in my junior year, and then almost all A's again in my senior year. And like that was a huge confidence boost to just be like, wow, I actually know what I'm doing. And then the important thing was not to just stop working. So when I got out of college, if anything, I was reading more because I could like do whatever I wanted. I didn't have to read for class. Aw, at what? Our timing is just a little bit off, so I don't know if it's... Often I have the same problem in other people's chats, too. I'm reacting to something, they're like, what? Oh yeah, she was huge in our math center. So she was working like, I don't know, like that was her work study job, was to do that one. And so I did AV services. So I was delivering like, LCD projectors and laptops and stuff like that to all the places around campus where the professors needed them. That was my job. Hers was much more academically focused. And had I worked there, right, I think I would have had a much easier time trying to figure stuff out. So I've never actually done technical writing until I had to do a report for my job. Basically, I was finishing the report at the start of the pandemic, and I got my report in on like the last day before we shut down. And then they were like, so by the way, we're not promoting anybody right now because we're in this kind of like limbo state. So just hang on to it, and we'll get you at the end, the end of the pandemic. I was like, great. So 2.5 years later, they finally did get back around to it, and that wasn't like the last contact I had. They said, we want you to edit this because it's pretty rough. I was like, no kidding. So I edited it, and they were like, yeah, definitely don't write like this, because that's way too technical for the like president's team. I'm like, oh. Mm-hmm. Yeah, my research paper in my senior year of high school was on black holes, which I blatantly plagiarized. But because I was smart about it and the teacher didn't care, I had basically like taken chunks like paragraphs and then summarized each paragraph as I did it. I don't recommend doing this, by the way. It is a terrible idea. It is very much plagiarism, and I should not have passed that class. Or, well, I shouldn't have passed that assignment. But because it was a technical subject, black holes, which I really loved, I just was having a problem. Like, I can't write is my issue. Like, I can write some stuff, but it sounds like me talking, which is not how you want writing to go. Yeah, don't use ChatGPT. Oh my god. On top of the fact that it says things that are completely wrong and with very much confidence. So, politician level. Stop. That's what they said about like our math classes too, and stuff like that. The upper level technical math classes. I ended up taking 2 education classes and 1 or 2 math classes in like the last few semesters because I was out of gen eds. My last semester was really great because we had senior seminar, which was all of us seniors getting together who are math education majors, and the professor said, so this is the book we're working with, and it's basically like math proof. So a sophomore level class, and he says, we're going to go through this, and we're all like, okay, like we've done this before. And he says, no, you're not learning it, you're teaching it to everybody else in the class. And I'm like, okay. So you have to go home, you have to lesson plan, you have to do this, that, and the other thing, and then you come back and you teach the next class. And then we had it set up in a rotation, so it was like, I think 1 person each week. And there were only 5 of us, maybe 7. I can't even remember anymore, but somewhere between 5 and 7. So we each got to do 2 and maybe a third, depending on how things were going. Yeah, CS is a very common program, but like not everybody, well, obviously not everybody can hack it. But not everybody can deal with like the course load either. That's what I meant, sorry. Not everybody can deal with the course load, but also like it's kind of a default for some people. They're just like, I think I want to do this. And it turns out that maybe they're not actually wanting to do that. They want to do something that has programming in it, but like these days practically anything can have programming in it. You just gotta like talk to your advisor and visit with other professors and talk with as many people as you possibly can to determine what it is you actually want to do with your life. And no matter what you get as your undergrad degree, like you don't have to stick with it and get a job specifically in that. I mean, look at me, I was math education, and I went off and worked at data entry for 3 years. Granted, while I was working at getting my master's in math or applied math, and also teaching as an adjunct professor. So as soon as I got my bachelor's, I tried teaching in the public schools for a year and a half, and that was like, eh. I was also a Kelly girl for a couple years there. And I just kind of picked up odd jobs doing whatever I could. So Kelly Services is a temp agency that works in the United States, and it used to be way back in the day that Kelly Services was originally a 100% like women typists who would go into offices and do whatever typing they needed, and then they would yep. I mean, it's always a question, right? Everybody's like, what do you mean Kelly girl? You were a Kelly, excuse me? And unless you know what the historical context behind it. Killer King! So again, Kelly Services used to be 100% women typists, and it was considered women's work to do typing back in those days. And I mean, obviously that is very anachronistic these days, and yikes. But I kind of made it a point of pride to because back in the day they would just be called Kelly girls, and so I was like, you know what, I'm gonna wear that with a badge of pride because I just think it's funny. And anybody who knows the story behind Kelly Services knows the Kelly girls. They also always wore green, like it was a green uniform. Raiding party! Silver, good evening. How's everybody doing? Good evening, Silver, and everybody who came over. I am Obi-Wan Pez. This is Simplex Pachinko. We are doing some math this evening. We've been talking about all sorts of fun stuff. Earlier on, we were doing the Simplex method of linear programming, which is no relation to me, by the way, which had to do with trying to find if you have multiple inequalities. If you have multiple inequalities, trying to find the optimal solution for a given objective function. And then we talked a bit about number theory, looking at the Chicken McNugget problem, and also the light switch problem. And then lately I've just been talking a little bit about my history in terms of like where I've been working, and the fact that whatever you get your degree in, it's going to be useful like no matter what. You just kind of have to find out what it's going to be useful for yourself. Yeah. So like I said, I was doing data entry for Kelly Services. And for anybody who wasn't here earlier, I jokingly call myself a Kelly girl, just because Kelly Services used to be a 100% women typist temp agency. Very nice. Congratulations. So, in theory, you can go from literally any college degree to literally any job that requires a college degree. Most of the time, they want you to have a degree in a relevant area, but quite honestly, if it's just a bachelor's or just an associate's that is required, it's not really going to be that strict in terms of like, oh, no, you must have a degree in our area. If you have work experience in their area, they're going to like that a lot more than just having a degree without any experience. This is one of the other reasons that your advisors and stuff like that should be telling you to try to get internships in your junior and senior year, or like, over the summer or something like that. You should definitely show somebody or tell somebody that you want to work in internships and try to get in there. Yep, right. Co-ops and undergrad research also count for that. Yep. Yeah. Yeah, typically without having with only having a high school diploma, a lot of the stuff these days has been relegated to or a lot of those jobs have been relegated to people without degrees. So manual labor, doing all sorts of stuff like that. And again, if you have experience in this sort of stuff, or if you just get your foot in the door in a company, service worker, yeah. If you get your foot in the door in a company, whatever company it is, you can work your way up, and there might only be some a couple of hard ceilings that you're not going to be able to get through without a degree of that particular type. Right. And it's always fine if that's what you feel like you want to do. All right, hang on one sec here. Be right back. Alright, I'm back. I know most of you are not back, so give it another few seconds here. Anyway. So yeah, Silver's absolutely right. If you can get a skilled trade out there, if you become an electrician, if you become woodworker or stuff like that, and you have good hard experience with running a business and or just doing the job itself, so making furniture, making doing electrician type jobs, you can make an absolute killing because nobody's going into skilled trades anymore. Everybody wants to go for college degrees and yeah. A lot of those people are retiring, and then we don't have anybody to replace them. My father, for example, is or was an aviator, but his original intent in college was to get some sort of, I think, engineering degree, and he dropped out of the program when he and my mom were, well, he dropped out in his senior year-ish and decided that he just hated it. One. Two, he and my mom decided to have me. And 3, he was just he was like, well, I can do whatever. You're gonna be a nurse, so Yeah, also technicians have a lot of issues with that sort of stuff, with like people screwing up on the job, and whether it's them or someone else, and that's a big problem, right? I wanted to go back here. Sorry, one sec. There we go. Okay, so Killer King, let's see. You had an actual question. Blainland, yes, you also have a question, which actually, Silver, you might be able to explain better if you're any decent at linear algebra, because I'm not. I don't know. Let's do that. Yeah. So it was, why can we find the column basis by switching the rows? It's like, why do we do that? I will say that my expertise lies much more in the other question, which was about trigonometry. So yeah, my dad actually was originally going to be an engineer. He dropped out of the program. They had me very young. They were 22. Mom was just graduating out of her nursing program. They got married. My grandmother was pissed. She later admitted to my mother, "I am so sorry, but I screwed up your wedding invitations on purpose because I was so upset with you." And my mom was like, "You did what?" I don't remember that. Nobody said anything. Like, okay. I mean, it could have been something as silly as, like, you know, spelling something wrong, or like, you know, I don't even know, like putting the time a half hour off or something weird like that, or maybe she just used a lower quality paper. I don't know. I never asked. But yeah, she was just like, I screwed him up on purpose because I was so angry. And my mom's like, what? This was the 80s, so I mean, Comic Sans wasn't quite a thing. Or, I mean, it was sort of a thing, but... Anyway, brace for silence. Welcome. Brace for science. There we go. Row space of the matrix should be equal to the row space of row reduced echelon form of the matrix. Yes. Yes, that makes complete sense to me. I don't know. Well, yeah, Loims, let me tell you, typo for new last name. Superbrain, if he were here, he would be laughing at that because he knows what name is. Yes, it is not something as long and convoluted as like Messerschmitt or something. I just, yeah. Airplane. Anyway. Going back, Killer King. So the double angle theorem. So if you have stuff like cosine of 2 theta equals cosine squared theta minus sine squared theta, or cosine of 2 theta equals 1 minus 2 sine squared of theta, or cosine 2 theta equals 2 cosine squared of theta minus 1. Yes, from memory. Just because I've done this so many times, it, you know, slightly on the edge of ridiculous. So if you have these sorts of things, it's not immediately obvious, and I will grant you that, where this can come in play. If you have an equation that is, and yes, this is slightly convoluted, or not convoluted, slightly contrived, but nonetheless, if you have an equation that is cosine of 2 theta, let's say it's like 4 cosine of 2 theta minus sine of theta is equal to I don't know, 2. Let's just go with something easy like this. Then one of the things that you can do is say that this is going to be 4 times 1 minus 2 sine squared of theta minus sine of theta equals 2. And now all of your variable terms are sine of theta, or in terms of sine of theta. So you get a 4 minus 8 sine squared theta minus sine of theta equals 2. Let's take all this and move it over to make sine squared positive. So 0 is equal to, this is going to be negative 4 plus 2 is a negative 2. 8 sine squared theta. Wow. Plus sine of theta. And now we have a quadratic. Right, so the sine of theta is going to be equal to negative b plus or minus square root of b squared minus 4ac, negative 2, thank goodness, all over 2a. Yeah, I'm good. So this is negative 1 plus or minus square root of 1 plus, this is going to be 8, 8 is 64, all over 16. So negative 1 plus or minus the square root of 65, all over 16. And that's equal to the sine of theta. So then theta is going to be equal to the inverse sine of that thing, or, and this is where some people get tripped up on this, pi minus that. So if you've already got the, inverse sine stuff, that's not too bad. If you have no idea what I'm talking about, that's perfectly fine. If you're kind of there, reason that this works is that when you're talking unit circle, really? You're not going to fix that circle? Okay, whatever. Oh, boo. Alright, whatever. When you're talking sine, you're talking the y values of this particular function. So if your y value is, let's say, 2/3 here, give or take, this is y equals 2/3. Then you're looking for 2 locations. One's going to be here, and one's going to be here. Your angles, by the way, right, this is equal to that. So your angles are supplementary to each other. Yeah. The one time I wanted to do something. So down here we can see that the square root of 65 is about 8. And so it's either plus or minus 1 from that. Well, okay. Negative 1 minus 8-ish is a little bit more than 9. Negative 9. Less than negative 9. So it's going to be negative 9 over 16-ish, which is within the range of a sine function. And if we add them, it's going to be 8-ish plus a negative 1, so 8 minus 1 is 7-ish over 16, which is also in the range of a sine. So that's why we definitely have two answers here. Okay, now if you're not satisfied with that one because, well, it's contrived, like why would you, well, right, that doesn't help. That's a little contrived. Why would you do that? You need something better, right? Okay, well, let's say that you're doing some calculus and you want to take the integral of the function cosine squared of theta, d theta. This is a super easy function. And if you want to go from 0 to pi over 2, this is going to try to find the area below this curve. All right, this is going to go back up over here and make more of these areas. So 0 to pi over 2 is going to give us this area here. Right, so here we say, okay, we want the area under this curve between 0 and pi over 2. So like, sorry, 0 and pi over 2. Let's get rid of that. That's at 1. Right, so here we're trying to take an integral of this thing. Now, if you've ever done any work with derivatives, you'll know that this is not a derivative of any particular function that you know just right off the top of your head. Right? It's not going to work out very nicely. So, what we have to do in the calculus side, and this is done in Calc 2 for the most part, but there are some places where you do learn some of this stuff in Calc 1. If you want to take the integral of cosine squared theta d theta, you can't really do this because what we would want to do is say that this is going to be a u squared. But then we have to have a du. Again, if you don't know what this means, that's perfectly fine. We just need the derivative of whatever u is as a part of our function. The derivative of a cosine function is a negative sine function, and I'm not seeing a negative sine function here. Right? We don't have any negative sine functions. So this is not going to work. It's an improper strategy for this particular one. However, if you remember your double angle formulas, you can say, wait a minute, I've got something. So the cosine squared of theta based on your double angle function here, if you just rearrange stuff, is going to be 1 plus cosine of 2 theta all over 2. This is just the double angle theorem, but they call it the power reduction theorem because it's telling you that it's going to reduce the power. It's doing what you want it to in this particular case. I don't really care, right, what anybody calls it. It is the double angle theorem, or a double angle property of cosines. And so we're just changing it, moving it around a bit to make it more convenient to what we want it to do in this moment. So yeah, power reduction, sure. So here this ends up being the integral of 1 plus cosine of 2 theta all over 2 d theta. And now we can separate this out and say, this does work. So we can take 0 to pi over 2. Right. What people call it is just basically what they need it to be in that moment. But, like, whatever. Right, so here we take the integral of a half. We end up getting theta over 2. And then we take the integral of a half cosine of 2 theta, and we get a negative 1/4 sine of 2 theta plus c. Well, not plus c, because we already got the... It's a definite integral, so we don't need that. And then evaluate 0 to pi over 2. Alright, for anybody who cares, pi over 2 minus 1/4 sine of twice pi over 2 is just pi, which makes the sine value 0. This is going to be pi over 4 minus all this stuff at 0 is 0. So that's it. Pi over 4. So the area underneath that curve right there is pi over 4. I kind of wish I could remember any of my complex analysis, because it'd be really cool to go over some residual stuff and show you the craziness of what happens when you try to take the integral of, I've mentioned this before here, but when you're trying to find the area under a curve that looks like this, nope. Ignore the hook at the end. An integral that looks something like this, we could actually translate it from x, y into the real imaginary plane. And as it turns out, it ends up being a semicircle. So that semicircle, and it pops up an ellipse. Give me a break, man. Right, so then you do area equals pi r squared, and then you translate it back into, right, area in the complex plane. And then here you have the area of the real plane is going to be this pi times, like, it turns out it's r squared, but it's going to be some particular value that transforms back from complex numbers back into real numbers. I don't remember if it's just absolute value, so it makes it real or whatever, but either way, you end up with something like 8 pi, and it's like, what? It was my absolute favorite class. So this was Master's Level 2, basically like your second year of being in Master's program. We actually did have a complex analysis class in undergrad, which was also cross-listed as you could either take it as a senior or you could take it as a Master's Level 1. Actually, it might be Master's Level 1 now that I'm thinking about it, but yeah. It was in my master's program. Whatever. So statistical inference, huh? I mean... So the absolute very basic idea. The absolute basic idea is that you first go and gather data from an unbiased sample. Now, this right here might be hard enough for you to figure out by yourself. How on earth do you make your sample unbiased? Given, yeah, good luck. Right, so you go for like a sample from the general population if you want. Somebody recently did a sample, I don't remember what they called it. It was for a sociological project, and I was like, oh my god. I think they call it a like unbiased targeted sample. So they specifically wanted people who belonged to a specific group, and then they said, let's get an unbiased sample of these people. And so it was just like, how would you even remotely get close to that? No, that's p hacking. That's different. So, like, they wanted to gather opinions of people who were within like car culture, right? So they wanted opinions for people who were within the sociological group of like car people. These are the people who like, buy cars and either race them or just take really good care of them, and they're like, performance vehicles. And they go hang out at like car shows and races and whatever else. Go racing at a track or something like that. So they only wanted to gather data from those people, first of all. And then they were like, we want to get an unbiased sample from within this group. And we're just like, right. So yeah, like I said, I can't remember the exact phrase that they used for it, but it was something like a targeted, unbiased targeted sample. And I'm like, are you sure is it truly unbiased? And then they didn't explain how it was unbiased, and I was like, nah, that's not going to work. Anyway. Eh. Probably. I mean, this wasn't like... The sociology professor signed off on it. But at the same time, it was like, you know, you're talking to a bunch of scientists about trying to get unbiased samples, and you're showing us that you, like, literally only collected samples from a certain group without explaining how it was unbiased. So, like, was it really a sample of convenience, where you were just like, I asked a bunch of people, and these were the ones who returned it? Was it like I confronted people and asked them if they would help me out by answering a question or two? Like, literally, did not help here. Or did not explain. So generally speaking, you're trying to gather data from an unbiased sample, then make inferences based on the data for that sample population, and then try to extrapolate that to the population at large, which again, you can't necessarily extrapolate it to the entire population of all people, but you can extrapolate to, like, based on this data, we think that, you know, car people will have these particular attitudes or something like that. Which Homer? Simpson? Yes, definitely accosting people in front of in a Target parking lot is the way to get the data. Gotcha. Hmm. Oh, that's a fun one. Admissions figures for the fall of 1973 show that men applying to University of California, Berkeley were more likely than women to be admitted, and the difference was so large that it was unlikely to be due to chance. Total applicants were 12,763. Their total percentage admitted was 41%. Of the men, there were 8,442, and percentage admitted were 44, whereas women numbered 4,321, and only 35% were admitted. However, they took the 6 largest departments, and they said in Department A, there were 825 men and 108 women. Of the men, only 62% were admitted, and of the women, 82% were admitted. In Department B, it was 560 men versus 25 women, and the difference was negligible, like 63 to 68%. Department C, 325 men and 593 women were admitted, and that made 37% of the men and 34% of the women. In Department D, 417 men and 375 women. No, okay. 375 women were admitted. Oh no, that's applicants. Sorry. Were applied, and 33% of men, 35% of women got in. So negligible again. In Department E, 191 men and 393 women applied, but only 28% of men and 24% of women were admitted. So in these two categories, Departments C and E, women only got admitted at 34 and 24% rates, but were made up so much larger of the population, it was kind of weird. And then Department F, 373 men, 341 women applied, and only 6 and 7% respectively got in. So again, negligible difference. But that was again a much larger percentage of the women even applying to this department to get in, but having so much lower of an admission rate. So that was the main group there, or the main impetus for understanding this paradox. So if you look at subgroups within the data, then it said the pattern may end up may end up completely disappearing, or be explained, or might even reverse itself, and like it's completely different. Good times. What was the ambulances one? Wonder if that's here now. No, that makes sense. Having worked a few years in an ambulance. I kept my feet on the ground though. Okay, let's do stacks. Statistics. That one's better. I'm lying. It's not necessarily better, but oof. That's a lot. They have a bunch of data in the back of the book. They're just like, go pick the data from Appendix C. Oh, man. Randomly survey 30 adults for the pinky finger lengths. Round the lengths to the nearest half centimeter. Construct a histogram, make 6 intervals. I don't really like this book. It seems so minimalistic compared to... I mean, maybe it's fine, and it's just stripped out all the fluff. Where are we? Pretty much at 12. All right. Anybody have any other questions? So that's the thing, right? I would assume it would go from, as long as you're consistent, it doesn't really matter all that much. I knew there was a reason I brought this out, right? Let's see. My calipers say that my pinky finger is approximately 5.26 centimeters long. So the kind of gold standard that everybody absolutely loves is Stewart's calculus. It is good. It is comprehensive. I don't think it has a whole lot of fluff to it, but at the same time, it does have like a lot of individual problems which may go above what you need. And you can always go older edition, right? That's the other thing. You do not have to buy the most recent edition. I don't even know if Stewart's alive anymore at this point. They did that with differential equations, Boyce and DePrima. Just saying. I think Boyce has been dead for 30 years or something like that. What's the... William E. Boyce. Yeah, died in 2019. Richard C. DePrima. So it seems like he's been maybe dead for a while. I mean, that's also true, honestly, is that you can go and find Paul's online notes and do very well just by using his stuff. Oh yeah, DePrima died in 1984, so but they were still using, they came out with the 10th edition of his book in 2000. Wait a minute, that can't be right. Can't be 2001. That's just got to be an old version. That can't be right. Hang on. Yeah, 2012. There we go. So the 10th edition of their book came out in 2012. James Stewart Calculus came out in 2015, was the most recent edition. 8th edition. So I think I had like the 2nd edition when it came out. Something like that. James Stewart, not Jimmy. It's very different. Yeah, he died in 2014. Canadian mathematician, violinist, and professor emeritus. So, let me... if we're going to actually pull some stuff, right? Let's... multiply, and then one example of that would be something like, this says that the life of a fully charged cell phone battery is normally distributed with a mean of 14 hours. Ugh. No. Ish. Closer. Okay, so a mean here, it's going to be 14 hours, and let's actually put the proper term in. Okay, so T. And a standard deviation of 1 hour. So this is going to be 15 hours here, and 13 down here. So our sigma is going to be 1 to either side of our mu 14 hours. What is the probability that a battery lasts at least 13 hours? So for this, what we really want is a z-score. Well, not really, I guess. What we really want is to figure out, right, what's our z-score? That's going to be mu minus x bar over sigma, I think. Which, of course, is going to make sense because this is freaking, right, it is the standard deviation. So, what we've got here then is, this is going to be absolute value. No, well, we don't need the absolute value, because we do actually want it to be positive or negative. Right, so z is going to be 1, which says that it's just going to be 1 standard deviation away from 1 standard deviation away from the mean, naturally. And then all of this stuff going on forever toward that tail is going to be included in this amount here. This is 1 standard deviation is 68%. Yes. Okay. So the stuff that is all within one standard deviation to either side represents 68% of the data. If it is truly normally distributed, you're going to get 68% of your data within 13 to 15 hours. There's going to be some that'll do less than 13 hours and some that'll do more than 15. But again, 68 is going to be within the middle section. 1 standard deviation to either side. Since we want the z stuff, which is going to be from 13 off to infinity, and since we know it's normally distributed, normal distribution says that we're going to have 50% above and 50% below our mean value. So this is 50%. This amount here ends up being half of our total 68% for standard deviation, so it's 34. Add those together, it's going to be 0.34 plus 0.5 is going to be 0.84. So 84% likely. This battery lasts at least 13 hours. Technically, it doesn't need to be the sample mean, so it doesn't need to be X bar. It can just be X for this. We just want to know what the sampled amount is. In our case, we said from 13 up. So we wanted to know what the z-score was for 13 itself. And that again was 1 because it's literally 1 standard deviation away. And then we said 1 standard deviation to the center is going to be 34, and from the center up is going to be 50. Okay. Other questions? So, Loyms, to answer your other question there, Stewart's calculus does, generally speaking, just have Calc 1 in it, but sometimes also Calc 2, depending on where your school draws the line. Paul's online notes is probably better. OpenStax is serviceable for calculus. It's not as pretty, not as flashy, but at the same time, it gets the job done if you are looking for a decent book. Calc 3 is definitely separate, so I know that much. Because our multivariate calculus, Stewart calculus book, was its own thing. Multivariable calculus 4th edition. Ew. So this one's specifically multivariable calculus 4th edition. And yeah. Used price $68.45. Oh, if only. Would not be the case these days. Yeah. Yeah. It starts with chapter 11. So it's telling you specifically that that is the at least second book. Oof. Sitting right on top of pre-hospital emergency care. Just in case. Ooh, that is my notebook. From... Oh, nope. That is my notebook from Stewart's. Yeah, maybe. No. This is an old calculus, or pre-calc. Yeah, okay. I got it now. This is my old pre-calc notes. And I was trying to copy down, like, all of the individual problems that I was doing out of our old book. As much fun as that is. Oh, and then here we go from the back. Yep, those are my actual teaching notes. followed by more problems out of the back of the book. Cool. Anyway. Yeah, calculate the slope of the hill so that you don't accidentally eject the passenger out the back. That's always fun. I get the Pilot's Handbook of Aeronautical Knowledge. I bet there's some good formulas in there we could probably prove. Alright, so I think for the next 40 some odd minutes or so, I have absolutely no idea what that is. Finite element method? I have seen something similar to this, but it wasn't on complex. Or is this not complex? Method of solving numerical method of solving differential equations. Interesting. Might be a bit much. Global stiffness matrix. Oh, there was a good one. I did this a while ago, but somebody had asked about Numberphile did it. Padé Approximants. Yeah, I'm not going to remember it, but... So instead of doing a Taylor series, so let's say you want sine of theta around theta equals 0. Sine of x around x equals 0. So rather than choosing a particular function, so the way of doing Taylor series, right, is that we say that we want f at 0 to be the same as our y at 0. We also want f prime at 0 to be the same as y prime at 0, f double prime at 0 to be the same as y double prime at 0, etc. And so when we do that, then we create this Taylor series of nth degree by saying we get C0 plus C1x plus C2x squared plus all the way out to Cn x to the n. So Padé Approximants says we don't need to do all that. We can do a rational function, which is going to be a sub 0 plus a sub 1x plus a sub 2x squared plus all the way out to a sub m x to the m divided by b sub 0, b sub 1x plus b sub 2x squared plus all the way out to b sub n x to the n. So the way that this works down here is that c sub n is going to be equal to, what was it? The nth derivative, yeah, at 0 divided by n factorial. I think that's it. Which for a sine function, right, c at 0 is just going to be the sine function at 0, which is 0. So Taylor, let's go 8 of x is going to be equal to 0, c sub 0 is 0. C sub 1 of x is going to be the cosine at 0, which is 1 over 1 factorial times x. Okay, and then we take a second derivative, we get a negative sign, which at 0 is 0. Oops. Another derivative is a negative cosine, so this is going to be a negative 1 divided by, that is the, oops, hang on, first, second, third derivative. So 1 over 3 factorial times x to the third. Right, obvious. Plus, and again, skip 1 because it's going to be a sine. Then we get a positive cosine again, so 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh plus, and getting it to the eighth. Okay, so we don't actually get 8 because that's just 0. We can do any odd number here. We'll just keep it as 8 because it doesn't really matter. So we get 4 terms out of it anyway. Now I'm not going to remember how to get A and B out of this, but cool. Oh, B sub 0 we just let be 1 so that we can't have any issues with division by 0. Again, not that it really matters, because it's fine. Literally says what the Taylor series coefficients are right there. Okay, cool. Cool, cool, cool. Yeah, I'm not going to remember what it is here, but I'll look it up here. Dr. Will Wood was the person I was thinking of here. I'll drop that in chat, because why not? So check that out if anybody's interested. That'll get you like how to create these sort of things. So how do we get A and B? It's been a while. Okay. So let's say that we only want a second degree Padé approximant. Then this will agree with the first n plus m terms of Taylor series. So if you already know what you're going to get for a Taylor series, like what we just did here, right? This is going to say that, all right, what we're going to get first is going to be x minus 1 over 6 x to the third. And then that's it. Because it only goes to x to the fourth, being this 2 plus 2 from our exponents here and here. So we're only going to get 4 as the thing here. So this is plus 0x to the fourth. Then we get a plus, he uses O x to the fifth, which is basically like an extra term, which is going to be like the overage or the error that we get for this particular thing. So then he says, we say this is just going to be equal to this a sub 0. Hey, top comment on that video is Grant Sanderson saying, hey, I've never heard of that. a1x plus a2x squared, 3 blue, 1 brown, if anybody doesn't, or only sort of remembers the name. All right, 1 plus b1x plus b2x squared. And then we multiply our quadratic over to the other side to get 1 plus bx1, b1x plus b2x squared multiplied by x minus 1/6 x cubed plus O of x to the fifth. is equal to a sub 0 plus a sub 1x plus a sub 2x squared. And then multiplying through, we get x minus 1/6 x cubed plus o of x to the fifth plus b1 x squared minus 1/6 x to the fourth I think more or less that's how it works, yeah. b1x times o x to the fifth. Okay, plus b2 x cubed minus 1/6 x to the fifth plus b2, wow, nope, b2 over 6 x to the fifth, and b2 x squared o of x to the fifth. All that is equal to the same stuff we had up here. A sub 0 plus a sub 1x minus a sub 2x squared. So here we're going to arrange by powers of x. We end up with any constants. The answer here is no. Everything has at least one x. So we have x. We have x squared. We got 1. That's it. b1 x squared plus b2 x cubed. Is that it? Yep. Minus 1/6 x to the fourth. That can't be it. b1 over 6 x to the fourth. And then here we've got a bunch of stuff that ends up being times x to the fifth or higher. And I could be wrong about this, but the stuff that's all x to the fifth or higher just ends up going away. We say that, you know what, it's times the o in some capacity, so it's just gone. Because essentially we've said that we're only going up to degree n plus m of the Taylor series, and so anything that goes 5th degree or higher we're just dropping. That's it. Okay, and then all of this is equal to, because we got the stuff on the other side, a sub 0 plus a sub 1x minus a sub 2 x squared. And then we have to do the old trick of matching up the coefficients for all the terms with like exponents. Again, unless I'm very much mistaken. Right, so a sub 0 is going to be 0 because there's no match on the other side for it. a sub 1 is just going to be 1. And negative a sub 2 is going to be equal to b1. I just randomly made it negative, so never mind. It's all, it's positive. It's fine. That's fine. I think probably it missed a stroke when I was trying to write it out. A2 and B1 are just the same thing. And then B2, x to the third has no counterpart on the other side. So B2 is just going to be equal to 0. Nope. Oh, there is a 1/3 there, right? Sorry, 1/6 to the third from the 1 here. So we do get that. Okay. So b to the third and a minus 1/6 there. B2 minus 1/6 times x to the third, so that means that B2 is 1/6. And then right. And then B1 is going to be 0 because it doesn't have any. Doesn't have any counterpart on the other side. So this is telling us that our sine of x could be approximated by a rational function 1x and b to the first, or sorry, b sub 1 is 0, so a sub 2 is also 0. Then divided by, this is very basic. Alright, 1 plus b sub 1 is 0, and b sub 2 is 1/6 x squared. Now again, this only works in like the immediate area surrounding this thing, but we got x over 1 plus 1/6, oops, x squared, right? One-sixth x squared, yep. So if we look at this in terms of the sine function, it's actually quite reasonable from 0 even up until pi over 2. It's not bad, like 1.57-ish. It's 1.113, so that's within, what? I mean, 11.3%. That value itself is not great, but you better watch out. I live in the mid-Atlantic. A lot of people don't appreciate that around here. My dad said that once in a post office. Don't recommend it. Alright, but again, now if we look at the Taylor series for this to the 4th degree, again, we only had 2 terms that were actually active in the Taylor series. Oops. So if we went with this, right? So that's x odd powers. So x minus 1/6 x to the third. right? This is the approximant, which is to the same degree. So we said it was out to the 4th degree, we got the same stuff. So if we wanted to go further and then make this plus 1 over 120 x to the 5th, right? In order to get this accurate, our approximant would need another degree on both top and bottom, or at least one in either location. So even if we did, this is probably going to change the entire thing, but nah, never mind. Yeah, it's going to change the whole thing. But if we calculate the Padé approximant to one more place, it's going to end up being more accurate than the Taylor series, if only just. So I actually did this out at one point and figured out what all of the individual stuff was going to end up getting us. And it was quite impressive at how far we were able to match this out to. And it is more accurate than Taylor series because we're using both our numerator and denominator to get this rational function, and it kind of balances everything out. So if we ended up doing, right, x minus 1/6 x to the 3rd plus 1 over 5 factorial x to the 5th, this would be, we could do this as any of the following, right? So we could have a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed over 1 plus b1x plus b2x squared, or a sub 0 plus a1x plus a2x squared over 1 plus b1x plus nope, no, that's good. Yep, b2x squared plus b3 x to the 3rd, or let's see if I can just do this. Usually can. Not cheating. Plus a3x cubed. Right, because here we've got our O can be x to the 6th, or O can be x to the 7th. Because our Taylor series, right, is either Taylor 5 or Taylor 6. So you can't necessarily tell which one it is. And so we could do something like this. In theory, we could also shift one of our degrees to either the numerator or denominator and make it 4 and 2 or 2 and 4. I think that actually causes some issues. So I'm pretty sure I tried it out whenever I did it. I'll try to find my notebook and see if I can, like, that might be my notebook. That'd be nice. No, at least not that section. Yeah, not so much. At least not that page, like I said. Pretty sure I know where it is, if it is in here, but it's quite possibly any one of the other random notebooks that I have written a whole bunch of math in. Yep, this is my original Colat's dungeon here. Lol. Not me. No, no. Nay, nay, says I. All right, let's play something. Probably not integrate now that I'm here. As awesome as it is. You know what? Let's do some character creation. It's gonna be terrible, but okay. So here's the other thing. I have had an issue with OBS tonight where it has just dropped off entirely. So if it does that, have a good night, everybody. If not, then I'll see you in about 2 minutes. Yeah, it's something between OBS and Linux. So for whatever reason, I tried to I tried to add 2 scenes. And so what happened was I was adding this window for the window capture, and then enhanceology. Sounds like you have a math question. Oh, we got several people come in. Everything through differential equations. With the exception of statistics, because I'm not very good at it. We can still walk through. I take it you two know each other. Or you're coming in from a different place. No? Okay. What's your question? Alright, that idea might get scuppered, but well, we'll see. Alright, so what are you trying to do? So if you're saying we want to find the something over a sheet. I may have to grab my Stewart calculus book again. Alright, so particularly double integrals. There's a lot of blank pages. Double integral 10 or 1003. I mean, double integrals will not be foundations of Algebra 1, but we can teach it. So if we've got some sort of sheet like this, what are we looking for? Be like the volume underneath this particular plane, well, non-plane surface. Oops. X and Y, dx dy. All right, DJ Vix boy, are you taking a piss or are you really saying that? Okay. So if we want, for instance, the sine of x plus y, let's just assume that it's something like this, dx dy, then the first integral inside integral is going to be our x values from, let's say, both of these are going to be 0 to pi over 2. Just for fun. volume of this particular solid is going to be, here we have the y integral from 0 to pi over 2, and then we're going to take the x integral of sine of x plus y. I mean, one of my teachers has made a fairly large step to solving it, and I do mean that. So the integral of the sine of x plus y with respect to dx is going to be a negative cosine of x plus y. So what we're going to do is treat any non-x variables as if they're just constants. Yeah, SATs are, they're something. Okay, go for it. Double integrals over general regions. Polar coordinates. Applications for density and mass. Inertia. Probability and statistics. Surface area. Next part right after surface area jumps straight into triple integrals. Right, so when we're doing polar stuff, we're going to say that we're trying to take an integral over a region that's going to look more or less like this. So our theta is going to start at some alpha angle, which is here, and it's going to end at some beta angle here. All right. Your r is going to start at A on the inside, lowercase r, and end at B, which is going to be the outside. Okay. I will help you with Algebra 2 no matter what. Let me know what it is that you specifically want, and I'll get it. Okay. So the area of this particular region R is going to be equal to double integral of It's not specifically the area. So here really what we're talking about is like, you know, there's going to be some particular like density function or whatever it is that we're doing. Most of the time it's going to be volume or something like that, where this is going like that. But it, yeah, it kind of depends on, we call it DA, yep. And this is our answer to whatever the application wants us to get here, whatever this might end up being. Yeah. All right. All right. So this also says that if this is not a convenient format for this to be in, which a lot of times XY is, but there will be certain ones where it's not actually possible to solve the integrals on X and Y due to the fact that, you know, if you remember from Calc 2, there's a bunch of integrals that we have to do numerical analysis on and can't actually do some of the nice stuff with. So instead, we can say, okay, we want this to be taken such that theta is going to be going from alpha to beta, and r is going to be going from a to b. And we change the coordinate system. So here what we're really doing is we're doing simple trig stuff. We said, like, you know, what's the sine of theta? Well, the sine of theta, if you remember the unit circle, got you that time. Right, drawing some random angle like this. Right, this side here is our x, this side here is our y, and this side here is our r. For a generic circle, it doesn't even have to be a unit circle. I take that back. Right, it doesn't have to be a unit circle. So yeah, DJ Vixboy, if you drop the question in the chat, I'll help you out next. Okay, so the sine of theta is going to be equal to, here we got y over r. Our cosine of theta is equal to x over r. Why, thank you very much for the follow. And that means that our sine theta is going to be equal to y, and our cosine theta is going to be equal to x. Which means that our function is going to be a function not of x and y anymore, but of r cosine theta and r sine theta. So that's all we're doing, is we're just exchanging x's and y's for r cosine theta, r sine theta, respectively. Alright, then what's happening is for any individual piece of this that we want to take out here and evaluate, what's really going on is that we're saying that this is going to end up being that works. Alright, so the dimensions of this thing, this rectangle that we want to get here, this is our d theta, this is our dr. And if we want to also look at this in terms of like looking at the area and how the area changes, we also need to look at the R, the radius that this is away from our origin point. So dA is going to be equal to R d theta dr. Oh, yeah, a better way to think of this, right, is that this is really d theta r d theta, or d theta r, and this is dr, and so you're multiplying r d theta times dr. So it's the area of that rectangle. Okay. So then over here this becomes f of r cosine theta r sine theta times r d theta. I have them the other way around. Got to be careful about which order you're getting these in, just for bookkeeping purposes. It doesn't actually matter mathematically speaking. Alright, so anyway, just real quick, my name is Obi-Wan Pez. This is Simplex Pachinko. We do math on Tuesday nights typically, and Friday night is typically game night. Tonight I skipped Tuesday this week, so you know, you skip the leg day, you got to do it harder in the later on in the week. So I was planning on doing a like split stream and do all that. Nah, it's been all math. It's fine. We're having fun. So next Tuesday, I will be back again to do more math. And then next Friday, we will probably be doing mostly, if not pure gaming. Most likely to do Skyrim character creation, because I have a crap ton of mods that I've put on and I want to see what it does. If it doesn't crash immediately. Sometimes been known to happen. And I've also been potentially doing or potentially starting Final Fantasy VII Remake Intergrade, or the intermission, because I haven't done that yet. We just finished up Final Fantasy VII Remake last week. So I was trying to argue with myself if we were gonna go ahead and do it, or if we were going to pass and then do something else for the next few weeks. I don't know. Okay, so we take this thing and we say, let's take, for instance, I have an example here that says we want to evaluate the double integral of this particular region. Ugh. Come on. With the function 3x plus 4y squared. Again, dA, just to shorten it up. It can be either dy dx or dx dy. In this case, it doesn't really matter. The two are going to interact well together, and when you're talking Calc 3, the x's and y's get treated like constants when you're using the other one, so it doesn't much matter. Alright, so if we go 3x plus 4y squared. Alright, we're trying to go from upper half plane bounded by circles. X squared plus y squared equals 1, and x squared plus y squared equals 4. So if we were to draw that on a standard xy plane, we have x squared plus y squared equals 1, and x squared plus y squared equals 4. Good enough. So here we want just this stuff here. At least I think so. Yes, okay. And y is greater than or equal to 0, and we're between these two circles. Cool. Half ring shown here. Cool. Okay. So this might be an overly simplistic example, but you know, we kind of want to make sure that we get it. In this particular case, we have r value, which is going to be between 1 and 2. Right? R equals 1 here, r equals 2 there. And our theta value is going to be between, this is going to be 0 to pi. Okay. So this also means then that we can translate this into this alternate form. Our x is r cosine theta plus 4 parentheses. That was weird because it also looked like my handwriting. That's bizarre. R sine theta squared and dA becomes r times all of it. R dr d theta. Okay, so let's do r as the inside one goes first. This is between 1 and 2. And theta goes between 0 and pi. Oh, yeah, DJ Big Boy. Sorry, I missed what your question was. Learning pretty much anything is going to help you with understanding some of the algebra that's behind it. Exposing you to this stuff right here is not going to help you directly, but, you know, it could be good for exposure to understand how all this works. Not the most brilliant thing in the world, but yeah, it'll be fine. Alright, so theta goes from 0 to pi. What's that? Okay, so over here, we're taking the integral from r, and that's going to get us a times 1/2 r squared. Our cosine of theta is treated like a constant because it doesn't have an r inside of it, so we just leave it as is. And then this is going to be plus. Here we have an r squared, so 4 times, take the integral of r squared, we get 1/3 r cubed, times sine squared theta. Oh, shoot. Nope. I did the thing that they said precisely not to do. I forgot the r on the outside here. So we're still going to have r going between 1 and 2. I mean, yes, definitely learning Algebra 2 will help with this eventually. But if you are seeing kind of how things are being put together, it can also help understand your algebra in the long run, of course. Okay, let's try this again. So 3r cosine theta plus 4r sine squared theta. And yes, I know. All right, this had an r here, which would then be multiplied into these pieces. So we now have 2 r's in the first term and 3 r's in the second term. Right, we get an r squared and then multiply by another one. dr d theta. Okay, so theta goes from 0 to pi. All right, so then 3r squared is actually just a nice antiderivative. That's r cubed. Cosine theta. Plus 4r cubed is a nice antiderivative. It's r to the 4th. I wonder why they did that. Sine squared theta. Okay, and then d theta is left because dr got used in taking the integral for the above stuff. Okay, then we want to take the integral with respect to theta. The first one's easy, the second one is less easy. So here I would suggest doing what we did earlier, which is saying that sine squared of theta is going to be 1 minus the cosine of 2 theta. All over 2. It's going to allow us to do literally anything. So this is going to be r cubed. The integral of a cosine is a sine. Plus, here we get r to the 4th times the quantity. This is going to be 1/2. And then this is going to be a minus 1/2 cosine of 2 theta. When you take the, let's just separate it out. Never mind. Won't do it all at once. Fine. Yeah, students hate it when I do that. Nope, 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 nope. Wait, what do you mean you did that? R to the 4th times the quantity, 1/2 theta minus. Here again, integral of a cosine is a sine, so that's easy enough. And then this is going to be 1/2 times 1/2 sine of 2 theta. Now this is evaluated where r is going to be equal to 1 to 2, and theta is going to go from 0 to pi. All right, so when we do the theta going from 0 to pi, notice that 2 of these things just kind of go away. Right, we end up with, and it doesn't matter what order we evaluate in, right? We can evaluate r and theta completely independently of each other. But it's going to be Oof. I don't recommend it. No, we don't get cross terms. Hang on. I know you can. It's not like you're supposed to, but all right, so r cubed times the quantity. Here is going to be our sine of pi minus our sine of 0. Oops, 0. So that's all 0. Right? Plus r to the 4th times the quantity. 1/2 pi minus 0 minus 1/4 sine of 2 pi minus 0. Or, sorry, 2 pi, sine of 2 pi minus sine of 0. So that takes care of all that, and then we also have the radius being evaluated from 1 to 2. So this is r cubed plus r to the 4th multiplied by pi over 2, and again this is all 0. So this stuff is just pi over 2. And then r is being evaluated from 1 to 2. So it's going to be 2 cubed minus 1 cubed plus 2 to the 4th pi over 2 times 1 to the 4th times minus 1 to the 4th times pi over 2. You can tell I'm slowing down a bit. Woo! Anthology, thank you. Last little bits out of that one. I mean, I know you can. You're still not meant to. Alright, so 8 minus 1. Plus, this is going to be 16 pi over 2, so 8 pi. Minus 1 to the 4th is just 1, times pi over 2 is just pi over 2. So that is 16 pi over 2, I probably should have left it. Minus pi over 2 is 15 pi over 2, and a 7. Okay. Yeah, I know it's expensive. Still. Woo! Alright. Questions? Ugh. I can't do coffee on an empty stomach. It rips up my insides pretty bad. Right, that is the question. So the answer has to do with it depends. So in this particular case, we could be trying to find a volume where the size going in like this direction is equal to 3x plus 4y squared. So if I wanted to visualize that's not what I want. GeoGebra. Should have known. Alright, so if we went 3x plus 4y squared. Okay. So this is more or less what we're seeing. Alright, it's a parabola in the y direction. There we go. It's also slanted along a linear equation. So our slant here is based on the vertices of all of the individual parabolas that are given by either this direction here. You can see them swooping down like that, or given by this horizontal parabola. Horizontal compared to our standard viewing window here. Alright, so then we said we had x squared plus y squared equals 1. And x squared plus, nope, plus y squared equals 4. So I'm wondering if it's also like equivalent to the volume of the shape that's just within, like within the region between the circles, where, well, they become cylinders in this particular case. But the other way that I've thought about this generally is that it's not really a paraboloid, but this thing that we have here has a density that's equal to our original function, which I have placed in here and you cannot see. Hooray. So our 3x plus 4y squared. Alright, so if that's a density, then we're looking at like what the volume of, or what the mass of this thing would be. Not volume. Alright, I'm reaching about the end of my useful ability to do anything here. Oops. Alright, I think I'm going to send us over to August Anomaly, who is playing Subnautica. She's got some new, apparently, chibi art or something, going for her VTuber thingy. And I hope everybody has a good weekend. I'm going to be spending the day tomorrow, or half the day tomorrow, doing a D&D game and try to not get my character killed. He unfortunately caught mummy rot this last one, so we'll see if he dusts or if we're going to have some sort of cure available. At any rate, hope you all have a good weekend. I'll see you all later. This is Obi-Wan Pez for Simplex Pachinko. Have a good night.